Hello, and thank you for joining us for today's webinar, Design for Manufacturability, DDM Changes the Rules. My name is Kim Kaloran, and I will be your host for today's event. For those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from 3D CAD files. Stratasys manufactures and markets Dimension and Uprint SE 3D printers, as well as Fortis 3D production systems that use our patented FDM technology. We also operate Red Eye On Demand, which is an online rapid prototyping and digital manufacturing service. In this webinar, you'll learn how you can be free of design for manufacturability constraints, and by doing so, how it can also help remove tooling costs and delays and continuously improve product designs, creating a better product overall. I'd like to welcome our speaker today, Bill Macy. Bill is the application development lead for the Stratasys Direct Digital Manufacturing Group, which is a team of experienced manufacturing technology professionals who act as a resource for manufacturers in high requirement, high certification industries like aerospace and defense. The focus of this DDM group is to develop innovative applications using FDM technology in traditional manufacturing environments to reduce cycle time, improve manufacturing cost ratios, increase design for manufacturing freedom, and reduce energy consumption. Bill's background includes 20 years of aerospace design and manufacturing experience, including mechanical engineering at Boeing and McDonnell Douglas. Bill holds numerous patents on modeling and manufacturing and has published several articles on reverse engineering. Prior to joining Stratasys, Bill built a manufacturing consulting practice working with military and commercial aerospace, automotive, and fabrication customers. Bill's key role at Stratasys is to help manufacturers identify how FDM technology can offer new design solutions that are not possible with traditional technology. Now, without further ado, Bill, the floor is yours.
Thank you, Kim. Appreciate the introduction and the opportunity to be here this morning to talk about DDM. So what is DDM? DDM is a method to create in-use parts directly from your CAD files. It'll allow manufacturers to skip the tooling process. What we found is that this can result in cost cut savings as well as your ability to speed up your production cycles. So particularly this applies to your low volume runs, complex geometries, and customized components. Choosing the right technology. Not all additive manufacturing technologies can provide DDM capability. You can evaluate the system based on a series of parameters. I'd like to suggest that you consider minimum wall thickness that the system can produce, the available materials that can solve your application needs, the accuracy requirements of your application, and then ultimately the surface finish that can be presented. Now remember that if your current prototyping technology is not suitable for end-use parts, DDM has a rapid return on investment, so you should consider how a new technology might provide you the opportunity to meet your DDM needs. So what is FDM? FDM is fused deposition modeling, where is a technology that was created at Stratasys. It is the process of using engineering-grade thermoplastics to build the part from the bottom up, layer by layer. It's that simple. To fully capitalize on the power of DDM, engineers should not limit themselves to the traditional manufacturing rules. There are many ways to manufacture parts. Today, I'd like to look at a number of ways DDM can provide new options to fabricate parts that would traditionally be made by injection molding methods. My goal is to provide you with some of the examples of how DDM can liberate engineers and designers from their traditional manufacturing concerns. Take, for example, draft angles. Injection molding requires draft angles in order to avoid ejection problems. Designing for DDM will free you up from those draft concerns. A part can even include a negative draft, as you see in some of the images on this slide. As a best practice, wall thicknesses should be consistent in injection molding to minimize shrinkage and sink marks. When designing for DDM, though, engineers can vary the wall thickness and even the density to suit their needs. I'll speak a little bit more about density in a later slide. Injection molded corners are often rounded to avoid mold stress and flow problems. DDM components can have sharp or rounded corners inside or outside of the part. This provides the designer with a lot of options to satisfy the functional requirements they might have to achieve. With injection molding, designers must commit to one material before the tooling phase to accommodate the characteristics of that specific material. However, DDM allows designers to switch materials as needed. Designers can build it out of a variety of materials depending on their design cycle they're entering. Say prototyping, an ABS and 30 material might be used to maximize cost and build time. When it comes time for an in-use part, they may switch to Ultim 985 for an aircraft interior part that had to meet FST requirements, that's flame, smoke, and toxicity, to pass a commercial aircraft application. This flexibility allows designers to readily transition through their design cycle. So expanding creativity. These new thought processes can help you expand your imagination to new levels of parts and expand your ability to create new designs. So we encourage you under DDM to iterate your designs, improve your product quality and functionality. As an example, I like to think about how easy it is to identify changes you'd make to your home floor plan after you've lived in your house. Prior to buying the house, you don't know what you want. Once you've lived in it, you can readily find the options you might change. The same is true of parts. Once you have them in your hand and can explore them, there's lots of options you might perfect and change how they work. Incorporate your customers' requirements without traditional restrictions that your designs might struggle with in the past due to the manufacturing process. Create more ergonomic products to improve your usefulness and customer satisfaction. We all know how good an iPod just feels in your hand. I'm sure that they went through many iterations before they found that shape and that particular design. With DDM, it allows you to go through those iterations to find those optimized shapes. You can also produce more custom and organic products without the penalty of traditional manufacturing. You can also race to market with your products to capitalize on new opportunities. I liken it to the example of T-shirts and ball caps after a World Series or Super Bowl. Companies are providing a product that's fully customized to the event or the circumstance at hand. Forget the old rules about design for manufacturability. Engineers can focus on the function without making compromises for the sake of speed, tooling, or simplicity. Designers can create beautiful forms and not sacrifice the aesthetics or character due to tooling limitations. Complex parts, when desirable, can be fast and practical with DDM. Working iteratively is another great value of DDM. By removing the tooling costs and the cycle time to produce tooling, DDM provides engineers and their designers the freedom and opportunity to continually improve their design. Even after the parts are in production, changes can still be integrated without the cost of new tooling modifications. In this figure, the tarp clip design, in the first iteration, the orange part, the tensioner was too loose. It wouldn't function correctly. In the second iteration, they were able to modify tolerances and gaps to improve the functionality. In the final black configuration, the part has been optimized to achieve the greatest functionality and performance for its customer. Question tradition. Many old practices and preferences stem from the original manufacturing constraints that no longer apply. In this picture, BMW needed fixtures for their assembly line. They readily had plate stock and handle stock that they could assemble to make a part to serve on the assembly line. With DDM, they were able to make much more ergonomic parts that were lighter weight, lower cost, and more flexible. They could actually adjust the design to improve the functionality for the operators in the shop. In this example, functionality was provided without the limitations of the stock material constraints they'd been saddled with in the past. Leverage DDM in your next product with these design tips. Make your parts feature-rich. Adding features no longer makes components more costly and time-consuming to produce. Don't strip down a design except to increase its performance or aesthetic value. The RPV, or remotely piloted vehicle, in this case an airplane, demonstrates examples of how very complex internal structures and the ability to produce parts ready to fly are a huge advantage in this market. In the case of Tape Wrangler, tape dispenser, the picture on the right, the customer needed to produce models quickly. Time to market is very critical. Tape Wrangler liked the high quality and fine feature detail they could achieve, but they really need to iterate their tolerances and their ability to produce the right gaps in the parts to make proper functionality. FDM offered them the ability to iterate these designs quickly and perfect their design for functionality. Rethink Walls. With DDM, wall thickness is constrained only by minimum thickness in your technology of choice. One part can have thick, thin, dense, and sparse walls. In the picture, the left side shows an example of a sparse-built structure. In FDM, sparse walls can maximize stiffness while reducing weight and their build times and material consumption. This is a strong advantage to maximize parts effectiveness as well as affordability. Consolidate your components. Because complexity is not a problem in DDM, designers can readily combine parts. This can eliminate assembly labor. I like to remind people that reducing shipping costs are not the only reason we see some assembly required on the products we purchase. Anybody that's assembled something at Christmas knows that story. It enables designers to tighten their tolerances. Fewer parts equal fewer interfaces that have to come together. An often overlooked savings is reduced inventory management. Finding the right parts built correctly at the right time can add significant cost and complexity to products. The illustration here shows a Bell & Howell scanner feed assembly. In this example, 26 parts were reduced to just 13. Another advantage of DDM is that you can move quickly. Move to your next project as soon as your design is perfected. You don't have to spend as much time to iterate additional design requirements for manufacture, like parting lines and draft angles. Lastly, never settle on a single solution for a complex problem. The great advantage of DDM is that design iteration to optimize a wide variety of solutions is possible. Prototypes for your ergonomic studies and functional tests are simple. The immediate transition of your design to production with a proven structural material is possible. The picture sequence here shows a Delta Airlines toilet stent problem. Delta Airlines had a maintenance and repair issue trying to keep these toilet valves from malfunctioning. The sheet metal part that's in the top figure was expensive and time-consuming to build. Finding an alternative design and a methodology that was producible and affordable was a tough problem. DDM was utilized to study a variety of different applications. You see 3 or 4 different configurations that were tested, evaluated, and then ultimately selected from to solve the problem. For Delta, they were able to reduce fabrication costs and cycle time, while savings were realized to improve part quality and function. And in the end, even the installation tool to put the part together was incorporated through DDM.
Great. Thanks, Bill. This has been very insightful. In a minute, we'll take any questions that you may have. If you have been thinking of a question in the meantime, please be sure to submit it through the Q&A panel. And I wanted to let you know that after the event today, you'll be able to find this recording. You'll be able to request the sample parts and download other relevant materials at the URL listed on the slide, www.stratasys.com/design-for-DDM. Okay, let's get on to the questions. It looks like during the presentation, a few have come in that we do have a little bit of time to take live now. Here is one, Bill, from Craig. He says, I'm new to the digital manufacturing world. Are there specific materials that are better suited for DDM than other materials?
Great question, Kim. It depends on the technology you're using, as well as the application requirements that you're trying to solve. Stratasys offers a variety of different materials that are targeted to specific applications. An example of that would be the Ultim 9085 material. This material was targeted for aerospace applications that require FST compliancy. On our website at stratasys.com, you can find all those materials and understand how those criteria are, what criteria are available for the material.
Sounds good. Here is another interesting question that came in from Scott. He's asking, you talked about design consolidation. Is there any benefit in segmenting parts with DDM?
Another good question. So a case in point would be like an architectural model. In many cases, they'll want to segment the roof from the floor plan so that a roof can be removed and you can see inside to see the different features that the architect is trying to communicate. In other examples, for applications where you have a part that needs access to a specific area, sometimes traditional manufacturing won't allow you the access to those parts. With FDM, you're open to new options, how you might provide that access doors, hatches, or even segmenting your entire assembly box.
Very good, okay. These are some great questions. Here is another one from Barb. How does designing for DDM change the design cycle overall? Can you go through the process overall briefly?
Sure. In general, every product goes through a series of steps from the time it's conceived to the time it's made available to users. It goes through the conceptual design, through a prototyping and test phase, a manufacturing phase, and then ultimately at some point it has to be supported. There's some level of support. Spare parts, different kinds of mods or changes that you can potentially make to the part you purchased. With FDM and or DDM, this application allows you to affect every one of those steps. So parts can be managed earlier as a prototype or test. It can be integrated into production faster because the elimination of the need for tooling. And then ultimately, as a part reaches its maturity, there's many options on how you can provide different solutions for those parts as a retrofit or mod.
Okay, great. Well, thank you, Bill. It looks like this is about all the time we have for today. Again, thanks, Bill, for your help with these questions. And if we didn't actually get to yours live on the call, we will be sure to follow up with you afterwards via email. We'd like to thank each of you for your attention during the presentation. And now I will turn it over to our operator who can close out the event.